should dress up as this.
Dress up as
Which I really like. I mean, I like this one.
more like
It's,
Make sure you have the jumper with that written on it.
yeah.
That's so true, actually. What do you think about the new group chat name?
I took these to select your shop, the Apple shop. And
not what I would have.
they are like crap.
Unfortunately, you don't get a choice in this.
It's £130.
Change it. It's Harrow now. Don't change it.
I can keep the picture the same.
No, I like the name. The name is what I'm.
I like the picture looks make you look like a gangster, like you look like
All I was dressed as a drug dealer for Halloween.
yeah, that's what I'm saying. It works. What about?
Oh yeah, we're going to be talking.
What does the asterisk mean?
I don't know. It just asks questions.
Yeah, okay. That makes you happy. There's no footnote there.
No, exactly. Yeah, what does it mean?
Square brackets 1.
It is so weird.
This is my normal line. But it's also kind of satisfying to wake up and like, you're fully rested. That's what it's
I'll kind of like 1 in the morning. I'm ready to be my classmates.
Oh, like,
Not even the one I know. One like an example above me.
you know what the average was for institutions?
I don't know for some.
What you should have done is gone out of your bed, gone upstairs and just knocked him out,
Straight off the
clean out.
Sorry, color can't be reached at this moment. I can't tell.
If I did sleep with bubbles actually yesterday.
Actually, no, I think what you should do instead of that is just woof down the phone, like start
I was like, a micro rap.
because then they wouldn't call back. They'd be like, what the fuck?
Yeah.
And then it was like, come to the front. So I went to the front. I went there.
Just do the thing like
I like that as well.
Do American Dad.
And it was just like,
I don't know American Dad.
actually, I wonder if I did the second.
I don't know. I heard there's a clip of a fish. What
Oh,
else?
it's a 40.
Did you find a clip like that?
I can find it.
I can never find a clip.
I'll find it. 50 of those.
I think the clip's a mess.
Do you think you name recognize
No. You might not.
Yeah.
Oh, yeah.
before we start, this is something that I did need to take care of, which is we will need a module representative. So if one of you is willing, one or more, then please get in touch with me. It doesn't require very much. It simply means that your contact details will be circulated, and you are probably going to be invited to participate in the department's group for module representatives to discuss issues with the department, and of course, to let me know of anything that students wish to communicate with me, which they do not wish to communicate directly. Okay? So I wanted to clarify that. Please put your name on that. Thank you. Questions before we start? Anything that you'd like to ask? Now, we were doing the proof of the first welfare theorem, and I'm going to continue with that. But before I go to that, there were two other things that I wanted to mention, which I didn't the other day. One of them is the following, that they're closely related. And this will be important when you get to problem set 2, where you have to work out the general equilibrium of a very simple economy. So it will be important for you to see how these things come to play. In what we've done so far, and in much of what we will do even for the next 2 or 3 days, one of the things that you want to remember is that if you have, say, a too good economy, then the behavior of the individual depends on the relative price. So although you have 2 commodities and therefore 2 prices, the most that you can do is determine the relative price between the 2. These are not 2 independent variables. The reason being, if you think of the budget line as the too good case, the position of the budget line is determined by the endowment together with the normal vector, which is the price vector. And if you multiply prices of all goods by the same number, then the position of the budget line does not change. You probably know that. That's called homogeneity. So homogeneity is a general property, which I haven't developed in class, but it's on the first problem set, which you can look at. I just have to make sure that I make it visible to students on the VLE. So that's one. So when you look for equilibrium, you cannot really solve for all prices. What you can do is solve for relative prices. Bear that in mind. So you have to, in some sense, fix the price level with the speed. The second is that since every agent meets his or her budget constraint, when you add them up over all the agents, you get a condition which relates demands across markets. Okay? So if all agents meet their budget constraints with equality, which will be the case in much of what we do, this is what everything that we do, it's because we will be imposing some form of conciliation or increasing utility functions, whichever way you want to think about it. What that does is that in the aggregate, you will, and this is regardless of equilibrium, this is important, because the budget constraint is something that you satisfy regardless of whether the prices which you face are equilibrium prices. The individual doesn't really know about equilibrium. The individual simply responds to prices in the market. Right? So if all individuals are responding to market prices, then the total value of their demand will always be equal to the total value of the endowment in the economy. Why is this important? Because this tells you that if you have equilibrium in all but one market, that last market must also clear. That's called Walras law. So at the end of it, you have homogeneity and Walras law. You have L markets, you have L prices. Homogeneity says that you can only determine L minus 1 prices. And Walras law says, well, it's all right, because you actually have only L minus 1 independent markets. The number of markets is equal to the number of price variables, the number of equations equals the number of variables that you're solving for, and a few other things falling in place, which you typically do, you can solve for the equilibrium. Is that okay? Any questions on that? Anything about that? All right. So we were looking at the proof of the first welfare theorem, and what we saw on Tuesday was that utility maximization implies cost minimization, provided you satisfy something like local concentration. In fact, in our case, it was exactly under local concentration. So now I'm not going to write everything out from here, but so if the equilibrium allocation is not Pareto optimal, okay, then there is a Pareto improvement. And so, a Pareto improvement meaning everybody's at least as well off in the alternative. Okay? So, Ui at the improvement, which I'm denoting Yi, is at least as large as Ui at the equilibrium, and 2 for some j, Uj, Yj is strictly larger than Uj, Xj star. From local non-satiation, we know that utility maximization implies cost minimization. This is what we showed. And therefore, we know that the equilibrium value of what the alternative costs must be at least the equilibrium value of the equilibrium consumption. And from utility maximization, we know that if you're looking at a point that gives you strictly high utility, clearly you could not afford to buy it. Okay? So here we have P star Yj is strictly larger than P star Xj star. Is that okay? Everyone? Please make sure that you follow. So now I can add these up, and I get, and I'm going to move one of these terms, or each of these terms to the left. So I sum over all agents, and I get P star times Yi minus Xi star is strictly positive. Is that okay? Right? Now I have a bunch of markets, so I can rewrite what I have written here as, do it for different markets. So I can write it as the sum over all my goods of the price of that good times, here I can write the sum over agents of what they demand of that good, denoted YIL. I want to make sure that the notation is the same as in the handout. So I can write this in this form and say that that is positive. Now why am I doing that? Well, only to say that this means that for at least one of the goods, the object that appears here is strictly positive. Is it okay? So this tells me that overall, what I'm spending on my alternative allocation is strictly more than what I'm spending at the equilibrium allocation. And therefore, in particular, for some good, I must be spending more. Okay? So since my prices are all non-negative, actually strictly positive here, there is a good commodity for which what is true? Well, this stuff must be strictly positive. For that good, sum over I of YIL must strictly exceed the sum over all I of X star IL. Okay? Where this latter is typically going to be the endowment over all agents. And therefore, you're allocating more of that good than you have in the economy. Is it okay? That's the proof. We've shown that under local non-satiation, if you start with a competitive equilibrium and you make the claim that it's not Pareto optimal, which means there exists an alternative allocation at which nobody is worse off and somebody is strictly better off, then it follows that you must be spending more at that alternative allocation. And if you're spending more at that alternative allocation, its prices are all non-negative, one of these terms has to be strictly positive. And therefore, for that good, you must be allocating more of that good than you are allocating at the equilibrium. And at the equilibrium, markets are clearing with equality, and this comes from the fact that, again, you have local non-satiation because of that. And therefore, you're allocating more than you have. If you're allowed to allocate more than you have, you can make people better off. That shouldn't be a surprise. Is it okay? Anything that's not clear about the proof? Questions? Anything that's not clear? So now what's actually happening here? That's the, shall we say, the maths. What is the economics behind all this? What's happening? We haven't really said very much. But there is a lot that's happening in the background. Technically, we said local non-satiation. But local non-satiation, of course, plays a key role here, but we can understand what local non-satiation is. Is that the only thing? The answer is no. What you actually need are the following. What's driving the result? What's in the economics of the result? Okay? It's the nature of the budget constraint. It's a single budget constraint. In everything that we've done so far, there is just one budget constraint. And therefore, it's very easy to say that if you have an allocation that improves strictly for at least one person and nobody's worse off, you can do all these computations with local non-satiation. So single budget, what does a single budget constraint actually mean here? So it says that in this abstract economy that we set up so far, the economy that we set up starting Monday, we just said, well, there are L goods. For each good, there is a market. It sounds sort of reasonable, but you'll see why it's problematic in a moment, a little later today. So for each good, there is a market, and the idea is you can take the value of any goods that you wish to sell and use it immediately to purchase goods that you wish to buy. There is no restriction on any such trade. Okay? That's key. All agents are, of course, price takers, so that's the competitive aspect, which is important. I don't know what you've seen in the second year, but you might have been at least told that when you look at Nash equilibria, it's not the case that Nash equilibria are efficient. Okay, or if you have, that's why when you have oligopoly or a monopoly, the outcome is not Pareto. The same reason is in the background, because there's strategic behavior. People realize that their actions will influence prices. Those are the firms. And the fact that they are able to internalize that means that they're able to, in some sense, manipulate behavior. That's why you get inefficiencies there. So that we don't have here. Okay? And we should think of promises made to purchase or sell as contracts that you sign. And your contracts have to be honored. You cannot say later that, oh, I made a mistake there, or something happened that you claim has happened which nobody else can verify. So there's symmetric information. And all of this will become much more important in the more general model that we specified. Is that okay? So that's the thing to keep your sort of eye out for. As I had said earlier, there is a second welfare theorem, which I had commented on the other day, so I'm not going to say much more about that. Okay, so there is a way of showing that if you don't like what the market is giving you, you wish to aim for a different Pareto optimal allocation. Even then, a very good way of doing that is by making transfers of income, call them taxes and transfers, and using markets to allocate goods, rather than trying to allocate goods directly by the plane. Okay? Now, what I want to do next is develop this abstract model that we have, I didn't write anything more there, but you have all the details in the notes. So, let's see. So I'm going to erase what we have here, so make use of the board, or better use of the board. So I'm going to put up a bunch of examples. And I'll show you in what way things change. So now suppose I have an economy in which I have two periods. So there is time, which is date 0 and date 1. 2 dates. Okay? At each date I have one good. So apples today and apples tomorrow or next year. That's it. I go back to my Edgeworth box. I have A, I have B. My goods are apples at t equals 0, apples at equals 1. I have an endowment, and in exactly the way we set up our economy at the beginning with just two goods, which I called apples and bananas, I can carry out the same analysis in this economy, provided I have a price at the beginning for apples today and a price at the beginning for apples tomorrow, and I allow people to trade. Is that okay? So I'm reinterpreting my Edgeworth box. So I'm reinterpreting my abstract economy and saying that, look, the two goods that I used earlier were apples and bananas. But what's really important for my analysis? That I have a market for each good, and on those markets I can transfer the value of my endowment from one to the other without any restriction. So if I have two markets that open in some sense at the beginning of time, let's say t equals 0, t equals -1, where I can trade apples, buy and sell apples today, and also buy and sell apples tomorrow, and transfer income, then I'm fine. This is just a particular case of what I've depended. Is that okay? You follow? Questions on that? Anything that's not clear? So that's one particular case. Now you might wonder a little more about how does this relate to trade, etc. Well, think about it now. Mr. A or Mrs. A, Miss A, has more of apples today than apples at the next date, right? So what is Mr. A doing here? That's how much they are lending. Yes? What do they receive? Well, in this figure, they receive a lot more, but that's particular to the economy. They might receive less, actually. Okay? So this is what they're lending, so that's what the other person is borrowing, and that's what the return is. The return has to be with the interest rate. So my prices in these markets define an implicit interest rate. You can make it explicit. You've done this, hopefully, in some of your classes. When you've written a budget constraint over time, this is price of apples at t equals 1 divided by the price of apples at t equals 0. So given the prices, you can work out the interest rate. Alternatively, an interest rate actually captures the relative price. You've all sorts of interest rates in the markets, those are financial markets. But there, if you write things out carefully, there is a way of converting them into relative prices. Is it okay? Yeah? Second example. Now, I'm going to reinterpret the commodities. I'm not going to draw another figure. I'm going to call my two commodities apples again, but if it is raining, and here if it is sunny. Okay. We call it an umbrella or a cup of tea, whatever you want to. Call it all sorts of things. So now, the story that I have here is both of these occur at time t equals 0, but I have two states of nature. Okay, so this is state alpha, and that's state beta. Is that all right? So my two goods now become the same good, but in different circumstances. And therefore, from my perspective, they could well be different goods. For example, it might be the case that when it's raining, the crop gets affected, and the quantity of apples that's available is actually much lower. The aggregate quantity of apples could be much lower. That's not captured in the box here, but you could think of it in those terms. That will affect relative prices. That will affect my behavior. Okay? It's the same model. The important thing is there is a market for each good. Agents are competitive in their behavior on those markets, and they can transfer income across these different goods in a single market at the beginning, which gives you that budget constraint. Without that budget constraint, you really can't do anything. Is that okay? So I can think of uncertainty. So I have time here, I have risk or uncertainty here. I'm not marking a difference here. These are situations which we typically call risk here. Okay? Because we will assume that agents have probabilities that they can assess and assign to the different events here. And those probabilities need not be identical across agents. They need not even be correct. Okay? But you can assign probabilities, rather than the case of uncertainty, where traditionally we think of those as situations where you cannot really assign probabilities to events. Okay? So these are all contingent goods. Contingent commodities. Time contingent or state contingent. We kept them separate so that we are able to continue thinking in terms of an Edgeworth box. Okay, so in this case, the important thing about states of nature, these are determined by, let's say, it's a state of nature. So no individual can affect what nature does. Your own actions cannot affect what nature is going to do. Okay, so that's an exogenous event. You have probabilities that you assess for those events. Those probabilities are captured in your preferences, and you behave on that basis. Okay. When you trade, you don't know what's going to happen. At the stage at which you trade, you don't know, and since information is symmetric, nobody knows what's going to happen. Right? The price that you pay can be thought of as the premium that you pay for an insurance contract. And in the event that, in fact, it's raining, you get to consume the amount that you've contracted in that event. You get nothing for the apples that you contracted in case it's sunny. Why? Because nature has determined that the state is, it's raining. You've paid up front. It's like any insurance that you buy. When you buy car insurance, right, you're required to, some minimal insurance, you get a payoff only in the case that there is an accident. You don't get to get your money back because you did not have an accident. The payment that you make is contingent on something happening. And you do it before you know anything about what will happen. Same sort of story. These are insurance contracts. The idea is that this very simple image that we see here of an Edgeworth box can be reinterpreted provided you understand what you are doing in terms of what are prices and what the budget constraint is, to allow you to deal with economies in which there is risk. Okay? Now, one of the things that I want to do here, because this will is something that we will need later, is put in state alpha, okay. State beta. So this, what I really wish to denote without developing a notation here, is the amount of the good that you buy in each of the states. Okay, so this is for any individual. We usually assume expected utility. It could be usually it could be a general form, but we often assume what is called state-independent expected utility, which is to say that your payoff from consuming a certain amount in each state is pi alpha u of x alpha. I don't remember how I've done it in the notes, etc. Write it in this form. Plus pi beta, which is your assessment, which of course is usually equal to 1 minus pi alpha u x beta. That's the utility function that you will maximize under expected utility. And the key property here is, given the form in which I've written it, you can actually look at an indifference curve and you can check for yourselves that the indifference curve will have the same slope regardless of where you are on the 45-degree line. Okay? This is an important property. So you can actually work out what that, so let me draw it a bit differently so that this a bit more accurately, so that it actually looks like a 45-degree line. Okay? So that line is the tangent to the indifference curve at some point along the 45-degree line. So when I look at the normal vector, that's my gradient of the utility, so that I can work that out from there. That's pi alpha, the derivative of u, at the point that I've chosen. But of course, since I'm on the 45-degree line, x alpha and x beta will be the same, but I'll write it in that form, u prime, x beta. And you see that since x alpha and x beta are the same, since I'm on the 45-degree line, the direction in which this vector points is independent of the specific value of x that I choose. So everywhere along the 45-degree line, I get indifference curves that are parallel. And this is a property that is important in determining the optimal allocation of risk in these problems, which you will have to do on the exercise. And you will see later. So I'm giving you enough so that you can work on it, and then I will show you how to make sure that you do it correctly. Okay? Have you seen a figure like that before in micro? Yes? No? Yeah. Okay, good. And needless to say, in the same way as over here, your endowments and preferences get reflected in the prices, here, beliefs and endowments and the utility function will get reflected in the prices. So prices carry information. Okay? Now all this was done with just one good at each date or each state. That's so that I can draw it on the board. There's nothing specific about it. The general model that I set up allows you to deal with everything in terms of many commodities at any given state. Free. Again, a very simple model. There is one date at t equals 0 and a second date at t equals 1. At t equals 0, there is a single state. At t equals 1, there are one of s possible states. This I shall call our canonical model, and I'll get back to that a bit later. Okay? So now, if I have just one good at each state, then I actually have 1 plus S goods in total. The first one at date 0, and S state contingent goods at 1. I can't put it on the board, I can't draw it, but it's captured by the economy that I started with. The general economy allowed for an arbitrary number of goods. The key point is whether I have the markets. Is it okay? 4. I'm sorry about this arrow here, which unfortunately cannot be erased. It's been written with a different kind of pen. Let's have an economy in which time goes on until some final date, capital T. There is no risk or uncertainty. An economy which goes on for many periods. No risk. You trade in exactly that manner, borrowing and lending, if you wish to call it that, over many periods. You could have many goods at each date. So long as you can write it as a problem in which all those prices of all those goods are available as contingent commodity prices in markets at an initial date, and you can trade there with a single budget constraint, everything that we have done so far goes through. Right? Clearly, our key assumption is that there is a single budget constraint. That's what's stretching our ability to accept this model as a reasonable one. And that's exactly what we will see. Okay? More generally, I can write or draw an arbitrary, it's called a tree. For example, I could have a single state at the beginning, splits into 2, rain and sun, splits into 2, rain and sun, splits into 2, rain and sun, etc. till I get to the final date. So I keep track of the dates at which it rained, and I go through my list. Such an object, so there is a mathematical structure here, is called a tree. Why? Because going to any of these points, which are called nodes, there is a unique point that comes from. That's the key property. Are you able to see that? Yeah. So the key property, I'm not writing this down. The key property is that when you go back, you're coming from exactly one node. In game theory, this is called perfect recall. You know exactly where you're coming from. The very standard assumption. More generally, I could have something where, in fact, perhaps there is one outcome here where, depending upon which side of which branch you take, after that there is no further uncertainty. This is just an example, and you end up there. Over here, you might have 3 outcomes, and then you proceed, and finally again, you will have a bunch of outcomes at date. That's a very general date event tree. What I'm trying to get across is you can think of an economy very generally, saying you have trade over time. At each point in time, you have different outcomes depending upon what nature chose. Those are your date events. You never forget anything. Over time, everybody learns more. And at the end, you have a bunch of mutually exclusive states of nature. Only one of them is realized, and you might have to wait until the end to find out. Okay? In this particular example, if you were to move to the right, then that's good enough to tell you what the final state will be. But that's just one possibility. That need not be what happens. In general, you might have to wait all the way to the end. At each of these date events, you could have a bunch of commodities that are available. Those are date and state contingent commodities. You will have an endowment of some of those because you might actually not live. Think of a macabre situation where half the people get knocked off if you go to the right here. There's no uncertainty after that, okay, but there was an earthquake there, and after that, just a bunch of people survive, and they continue to trade forever. Okay, so the rest of the people don't have any endowments or preferences there. That's fine. In some sense, birth and death are allowed in this economy. Somebody might be born halfway down the tree. The important thing is to begin with, everybody can trade at an initial market. That's key. Is it okay? Making sense? It's sort of tough to accept that that's any realistic description of the economy. But of course it isn't. It's a model. It's a model that's used as a benchmark, and you'll see very soon as to why it's a benchmark. Very, very soon. So what we are describing is something called the Arrow-Debreuil model. Arrow is considered to be one of the greatest economists that the world has seen. Died a few years back. He was, for many years, the youngest Nobel laureate in economics. He started as an undergraduate in maths, like many economists, also people like Cadence, but Arrow did that in New York. And he wanted to become an actuary. And somebody who was one of his teachers, actually, an economist, said to him that you can do more things. Stay in academia, and he did. You might know that York is very famous for health economics. Arrow wrote what is considered to be the first paper in health economics. He wrote only one, but that was good enough. Okay? Debreuil was a French mathematician who turned to economics. He won the Nobel Prize many years after Arrow. Okay? And the model that we've developed, which, what I've said is actually all that you have. You have a general structure of dates and events which is given to you. That's exogenous. It has a minimal requirement of consistency, which, as I described, says that from any node, you can trace your way back to the beginning through just a single path. That's the idea. I stated it as you know exactly where you came from. But that's what's happening. So it really looks like a tree with branches out as you go further down in time. So that is given to you, and at every date event, you're given a set of commodities that's available, which has, each commodity has the characteristics that we described earlier. Okay, so completely defined. They can be distinguished by what they are, and in this framework, the commodity is one that you use at that date event, and that's it. It's perishable. I haven't said anything about production. You haven't brought in firms here. You can bring in firms. There's no problem. You can do that. Firms with private ownership firms, firms that are owned by people. Okay? So you will have those commodities, and then based on the set of commodities that you have, you will have agents with their characteristics. So commodities that they will consume in certain combinations, their consumption sets, their endowments, their preferences, and the key property. There is a market for each and every date contingent commodity where you can trade. And you can trade without restriction. So income that you're supposed to get, if everything turns out really well in your career, 30 years down the road, is something that you can actually trade with today. That's what makes the model completely unrealistic here, because those markets are missing. Is it okay? But if you have that market structure, then the abstract economy that we developed on Monday and Tuesday is one that you can use. And you can use the first welfare theorem. You can say that competitive equilibria in such an economy will necessarily be Pareto optimal. There is no role for government intervention, there is no role for money, there is no role for any of that. Because you've assumed that you don't need them by setting up the structure in such a manner. Is it okay? Are you making some sense here? Are you following? Yeah? So, I just want to make sure that I'm covering the things that I wish to say here. Now, I haven't written down any of this, much of this formally in terms of what is an economy. An Arrow-Debreuil economy, as I said, the key property is the set of commodities, and you have all that in the notes, which is why I'm not writing it. You're welcome to ask me questions on Monday, for example, on anything that's not clear. The key property being prices, etc. And now I'm going to write that here. So, with reference to, okay, so, pen isn't working too well. Specify a date event tree, list of commodities, and each node in the tree generates script L set of commodities. Your economy will be given by your specification of commodities, which has built into it the date event tree now, and therefore for each agent you will have a consumption set, a utility function, and an endowment. That's an economy. There will be a price, date, and state contingent for each L in the space of commodities. The interpretation is again one of insurance. Right at the beginning, you pay these prices for goods that you wish to buy in some date event contingent commodity. If you look at markets for oil, for example, this is probably the best example. There are other markets for commodities, agricultural commodities, etc. But particularly for oil, you have oil. If you look at details, you don't really have it for every point in time. But you do have oil for trade, a specific kind of oil, type of crude oil, for trade even 8 to 10 years out. Okay? So those are examples of the sorts of commodities that we have in mind. Where again, you pay up front for what you wish to buy or what you wish to sell, you receive payment, but delivery is made only if that contingency occurs, not otherwise. So this is a contract that you make. Okay? And just keeping track of the time here. So there's an initial date before date 0, shall we say, so date -1, at which all markets open. That's where all trade takes place. And no trade will take place after that. There is no need for any further trading in the Arrow-Deborah framework. You do it once and for all. The reason is your preferences are consistent. As you move through time, as everybody learns a little more, there is nothing new that you learn which you had not anticipated learning. Which is why there is no reason for any further trade. And these are sort of important points which you're not going to be asked on the exam or anything like that, but which you might not find in various things that you read. Okay, there's very few references here that actually do a good job of explaining these things, unfortunately. There are some of those are listed. But it's more important for you to get a general picture of what we are doing here. Okay, so the key issues are, first thing is the first welfare theorem holds under local non-association. And the key properties are market for each good, and the commodity here is a date contingent commodity, which I'm not writing each time. Market for each good, single budget constraint, points that I've made. Price taking behavior, of course, and again, something that I've mentioned, all contracts are honored. So there is no asymmetry of information. You cannot claim that, oh, I said that I'm going to deliver 300 cars if such and such thing happens, but such and such thing did not happen, so I'm not going to pay up. Because somebody else can verify whether or not such and such thing happens. Courts can verify that, and that's crucial here. Obviously, if you did not have verification, then the other side in the market would not sign that contract with you. You wouldn't sign a contract with somebody where they have an advantage in information, unless the price is different. Is that okay? So all that is very important here. Now that's the good stuff. Right? The bad stuff, of course, is this is completely unrealistic. Look at all the markets that you need to begin. You just don't have these markets. Not only that, even if you have all these markets, lots of people will not be able to trade on them. Okay? And as I've already said, there is no role for any intervention. There is no role for money. Now, what we are going to do from here on is focus on this so-called canonical model. So we are not going to think about the general tree structure, because everything that we can do there, the insights can be obtained from that model. Okay? So that's the model that we're going to use. We're going to move to a different market structure, which is much more realistic. And the next question is, in that realistic market structure, when is it that you get Pareto optimality? Okay? That's what we're going to do. And for that, there will be some notation. Okay. So the notation is something that I will start with on Monday, very briefly, but it would help if you've looked at the notes for that, so that we can work through that and get to the meat of the problem. Is it okay? Questions? I hope you're liking this, but I'm fully aware that, as I've said right at the beginning, and I've repeated, for much of the first few weeks actually, or even until the end, you will find the material to be very different, difficult to grapple with, etc. But that's part of the idea, is to get you to think about these things. And ask any questions that you want to. Somebody who came and met me on Tuesday for officers, okay, I don't say that all of you have to, unless you have questions. It would be a good idea if you start thinking, you have questions, because you will see that there are things that you might think you've understood, but actually you haven't, because there's a deeper way of understanding. Discuss things amongst yourselves, if you do that. Okay? We continue on Monday.